Good evening here in Brazil. I believe it's good morning there. I'm here to talk a little bit about advanced human robotic interaction strategies for walker-assisted gait. I am Anselmo Frizera, and I am an electrical engineering from the Federal University of Espírito Santo. I graduated in 2006, and after a short period in Spain, where I did my PhD, I came back to Brazil, where I'm a professor since 2010. Here we work in several different areas, but pretty much in biomedical engineering and rehabilitation robotics, and work and trying to integrate human robotic environment interaction, cloud robotics, and different types of sensors into new therapies and assistive technologies. Our university is medium-sized university for Brazil. We are about 25,000 students, 2,000 professors, and 2,000 administrative staffs. And we have experienced a nice growth in the last 15 to 20 years. So we are also located in a very nice and warm weather here in Brazil, where we can have very nice landscapes. And if you want to visit us at any time, we'll be very happy to have you here. Just to be short and to get into the subject, our main concern here in my group is to develop technologies that help people that have mobility conditions. And we work on stroke, spinal cord injury, and cerebral palsy. But we are very worried here in Brazil with the conditions that we have for the elderly population. What happens is that we expect a very important growth in the elderly population in Brazil and in Latin America in general, and we do not see any modifications in the health systems or any growth in the physiotherapists available to treat and assist these people when this time comes. So we do not see a national policy to improve the quality of care of the elderly population in Brazil, and we are already experiencing some shortage of professionals in several areas. So as electrical engineers, we try to develop robotic systems, devices and photonics sensors and photonic devices for monitoring several conditions, and try to develop also signal and image processing techniques as a way of an electrical engineering contributing into the bioengineering group. So I want to make just a very short presentation of the sensors that we develop here, and then we focus more in the second part on the rehabilitation robotics. As we see a growth and an evolution of the interaction between human and robots, right now we understand that for an efficient workforce, human and robots must cooperate very closely. So there are very new interaction strategies that can take advantage of the high dexterity of humans and robotics working together. And we understand that soft robots will be very important in these next evolutions. Soft robotics are also very good because they can absorb energy and they provide stability. They also can integrate intelligence into the construction of the robot, and they are very safe to operate close to the humans. So there are many safe soft robotics being developed now for several areas, and we are trying to develop some solutions that could be integrated into wearable devices and assistive technologies, such as the ones that we present here in these images. But we understand that there are important challenges that should be taken into account in order to achieve actual benefits when developing soft robotics. In our case, we try to study sensor solutions. And in this sense, we understand that optical fiber sensors are very interesting for being integrated into soft robotics, especially considering that we have electromagnetic field immunity, we have multiplexing capability, very small dimensions, so we can develop, especially considering the plastic optical fibers, and polymerical materials, devices that are very flexible and easy to integrate into smart textiles. So in our group, besides from the robotic devices, we are developing very new sensing devices for integrating into shoes, into clothes, pants, and actually into soft robotics. And these applications will be presented in a future opportunity. Right now, we want to focus on rehabilitation robotics and assistive technologies. And just as we see it, there is no way that a robot will fully replace a physiotherapist because we understand that the conventional therapists are performed by the best machines. The humans are actually very good not only on providing physiotherapies, but also in the motivations. And we understand that physical contact in human contact is a key aspect for this kind of rehabilitation. Nevertheless, the alternative, and especially the robotic therapies, allow quantification of progress, and we can actually provide very repetitive strategies. This is important, especially here, where physiotherapists need to work lots of long hours, and it's very hard to have a consistent therapy all the time. In this sense, for developing rehabilitation robotics and assistive technologies, we need to understand the human, fully understand the intention of the human that's controlling the device. And here we provide several human-robot cognitive interaction strategies. We actually need to provide inherent safety, and physical interaction is very important. And usability is a key aspect here because we actually develop many solutions, but to achieve something that's actually usable for the user, it's quite hard. We like to take this first prototype that was transformed into a commercial solution. This is a standing frame developed by a research group in Spain where I did my PhD. This was like my first work as an electrical engineer. And we developed this prototype very fast. And in 6 months, we had like a very stable device. But to transform this prototype into a final solution, a commercial solution, took us almost 4 years. So we can see how hard it is to get an actual usable device where it's easy for the user to take it to the home and charge and warranties and have assistance from the companies to work. So this was one of our first projects, and I'm very proud that we could actually take something out of the lab and have this standing frame developed with the users in Spain. But then the main topic of my talk is to address the smart walkers. Here we provide a timeline of the evolution of these devices in the groups that I'm working on. And the first one in the 90s, before I started working on this topic, several researchers showed that just by providing a motorized control of the device present many clinical benefits, such as many clinical benefits from this controlled movement of the device. Also, the partial body weight support provided by the walkers actually enable safer locomotion for people with locomotion impairment. Afterwards, in 2006, we developed a natural human-robot interaction strategy where we were able, just by understanding the interaction forces and the leg movements of the subject, we were able to predict what they wanted to do and to extract what was the intentional movements and separate this from the unnatural gait patterns that were caused by the stroke or the spinal cord injury, and we use only the intentional movements to control the device. This device was experimented in the National Hospital of Paraplegics in Toledo, and we had a good, successful interaction there. And after that, we just started to working on two fronts. In Portugal, in collaboration with Professor Cristina Santos, we developed a low-cost structure and electronics for clinical validations. And in Brazil, as our group is more focused on robotics and electrical engineer, we started to develop different prototypes that were more focused on control and cloud robotics. So we just will try to pass through these prototypes and show to you what we have done in the last years. So this was the first one. This is the Symbiosis walker. This was developed in Spain. And what we did here is extract the movement intentions just by developing let's say, special filters to extract what was intentional and what was not intentional for the user. And we applied these in patients that were being that lived in this facility in Spain, where they were being part of a rehabilitation program. The idea here was just to show that a smart walker could be integrated into the everyday therapy, and the patient was able to control this from the first time. The idea was to develop some natural interfaces where no training was necessary. So we used several different interfaces here. We measured the interaction forces in the upper limbs, and we also measured the leg movements in the distance from each leg to the walker. And we use this information to modify the interaction and make the walker follow the users in the front. After that, here in Brazil, we started to develop different techniques just to demonstrate mathematically and in practical experiments that the device was not, that we could achieve robust control interfaces. And here we show that the person's walking, and with no physical connection to the robot is able to follow the person in front of the person. So here we show that the person is in control of the device at all times. After we achieved a good human-robot physical interaction and cognitive interaction, we start moving towards the environment. So we understand that this person with the walker needs to interact with other people and needs to safely move around in unmapped environments. So we started to install other sensors such as laser scanners and cameras, and we started to develop some interaction strategies and mapping strategies to make this locomotion safer for the subject. Here we show some results of our work. So here we integrated spatial modulation and social interaction and prosemics in walker-assisted gait. So what we want to show here in this first video is that the person is walking with another subject. So we don't want a patient not to be able to interact closely with another human. So we want this interaction to be natural. But when these interactions become dangerous for the subject, each one of them, the walker user or the person that's walking with him, we modulate the impedance so it's harder to move towards the collision. So we never move the person around, we actually make it harder for the person to collide. So here we are modulating the impedance, and when the person starts to move into different areas, interaction areas with the robot, we modulate the impedance. So this guy with the green shirt is just causing these complicated situations. Here he just stopped in front of the walker. So the walker offered low impedance, mechanical impedance way for the subject. Nevertheless, we can have much more extreme situations like it's going to happen now. So the person is just going to stop very close and cross in front of the subject. And here we can see that the interaction forces actually change because the modulation, the impedance is being modulated until we have like a very extreme, so the person, very extreme situation when the person is walking towards the device. In all these cases, the walker was able to avoid the collision by providing a low impedance pathway for the walker subject. And we tried this with many complex situations, with many people walking around, and this was actually a very nice result for our group. More recently, we also tried to integrate visual strategies for visually impaired people in complex environments like we can see here, and these environments are not mapped. We have a system that's able to calculate the pathway that we want the subject to walk. and then we create a kind of virtual trail, so the person is not able to not walking within the trajectory, but he's choosing the velocity and he can feel the change haptically. So here, when he reaches a corner, the walker becomes harder to move forward and easier to turn. And here we can just show him, this guy is not seeing anything, haptically we're able to show him a different way and he can move from one room to the other with no difficulty. After we started to integrate all this human-robot interaction and environment interactions, we started to get a lot of processing power that should be installed into the walker. And we understood that this makes the walker expensive. And actually, we have like different batteries and we need more processing power. So we started to move everything to the cloud. And the idea here was to develop a very simple device using these aluminum profiles that are very easy to buy. And we only used materials that we could get out of the shelf. So if you see here, we have 4 sensors, we have webcams, laser scanners that were not very expensive, and we also have power banks for as power supply, and this kind of motorcycle batteries for the DC motors. And the electronics were just Raspberry Pis or Beagle bones or very simple boards that we could just go out into the store and buy it. And everything would be, all the processing power, the complicated stuff would be in the cloud. So in the local functions, we only provided physical assistance and low-level control and very important safety rules or security rules to avoid collisions. But when we have a good connection to the cloud, the device was able to provide advanced control strategies, distributed mapping. So here we could have many devices walking and moving around, and we can make a collaborative maps. We could make traffic control, so we could avoid different difficult areas. So if you have a walker or a simple robot into a certain area of the hospital, for example, and this area was very crowded, I could just change the interaction strategies for the other devices that were around, and we could control this traffic inside the hospital. We can make patient assessment tools, medical reports, and more sophisticated cognitive assistant strategies. Uh, for this to work, we needed to understand what were the services, the quality of service necessary to have a good experience. So what we did here is simulate different connectivity situations like losing packages or latencies and different cloud conditions that could uh, that could provide a bad feeling or experience to the user. And we started to evaluate what were the minimal conditions for the net service that would allow a good connectivity and a good experience for the user. In this case, what we did was make a virtual cloud. We put 2 computers in the same walker, and we just mess with the network on purpose. And then and then by making many experiments, we could identify the good network conditions for our robot to operate into the cloud. And in this case, we can decide if we are going to rely on the local controller, or we could rely on the service provided by the remote platform. And after that, we were able to integrate many new solutions. So in the first video here in the top left side, we are showing admittance control and human-robot interaction strategies without contact, without any contact with a person walking in Colombia. So he's guiding this robotic platform just by moving the head and by getting closer or farther away from the robot. So we're just measuring head movements and legs, and the controller is being executed here in Brazil. So we were able to provide a good quality of service remotely. In this video in the bottom, what we are showing is that this robot was able to go to a room, find a person, and then offer assistance just by having a very simple webcam, and we could identify which was a door or a person or a table, and then find a certain person and go towards this person and offer the service of the robot. So this was very interesting for us, so we could demonstrate that it's possible to integrate deep learning models and very sophisticated strategies into a very simple platform. And here in the last video in the center, we are just walking with the device in a new environment, and we are providing a mapping solution in real time. And then we are uploading this map into the cloud. So if we have another robot close by, he could use this new map, dynamic map, in real time. After that, we started to integrate more artificial intelligence strategies to the device. And the idea here was to make the robotic device easier to understand by the subject that was we using. So we started to integrate behavior trees here. And when the person was driving the device, we were able to show to the person which strategy was being used in any time. So for example, here we have a very fast video. This person is walking, and we only have here a very simple admittance control, but the device detects an object. So he tells the user that he's going around this object, so the person knows that there was an obstacle avoidance strategy. Here now the person is walking, and it's not the same that we have a human subject or an obstacle in the same time. So here he takes a human, and he can choose to interact with this person or choose to avoid this person. And as the person moves to another position, the robot is also free to communicate to walk around. And here we show that we could have a very dangerous situation, and the person's warned that we just change the behavior. So the idea here is to provide a visual representation to the user of what's going on with the device in a way that we could train this person and make the device easier to understand. So behavior trees was chosen for this purpose. Right now, what we are doing, this is our last development, is we are trying to combine virtual reality with Walker Assistant Gait in order to provide more sophisticated and more interactive and training scenarios. And the idea here was to work in two different scenarios. The first one was a treadmill, and using the same sensors, which was a very simple LiDAR, laser rangefinder here in the legs, and two force sensors. We were able to train the user to use different interaction strategies, but in a very safe situation. He was in a treadmill, and we can actually use some partial body weight support devices so the person can walk safely, and we can control this weight in the treadmill. And the idea here is to provide interactive scenarios here with this projection, and the person is able to walk safely and understand different strategies. The second scenario was to put the person in a virtual reality while walking with the device. What we can do here is in a big room, offer many different situations, like the person can be inserted into a home or into a very complex environment, and he can feel how the device would behave when avoiding obstacles or when interacting with other people without the unnecessary risk of actually being there. So the person is walking with the device, and we are modulating the impedance and changing and trying different interaction strategies without the necessity of creating these environments physically. So we started to do this in the last month. This is the very new results for us. And what we have here, we have the actual walker, and we have a digital twin. And when the person is in this virtual environment, he is walking here, we are able to show him we are able to show actual physical obstacles with this red point. So the person knows that here in this area, we have actual physical objects in front of him, so he's safe. But we are also able to put like this box around here, which is a virtual object. And we can make real and virtual sensors interact with real and virtual objects. And we can create very complex scenarios and serious games, so we can motivate more the subject and create very interesting games and scenarios to play. And this can be taken into the rehabilitation clinic. So the idea here, one was our first experiment was trying to make the person discover a certain path within an environment. So I need to go from point A to point B, but I create a very low impedance, physical impedance, mechanical impedance pathway to get to point A from point A to point B. In this case, the person has to discover this trajectory and where we are going to make these turns, and we present it to him physically. So here in the first one, in the left side, he's just having this haptic feedback, and on the right side, he's actually being the trajectory is actually being shown to the user. So of course, here I'm able to follow this trajectory with much more precision. But the idea here is that when we train the person with this controller, he can feel how the control behaves to follow a certain path. When I take this visual cue away, the person actually can learn how to better interact with this controller, and we can fine-tune the control to the user at the same time that the user is trained to better use this controller. We have here some examples of other strategies that we are actually validating now. Here we have the subject supported by the device, but we do not want this person to be not well positioned on the walker. So we want to apply a certain partial body weight support strategy, and we want the subject to be within a certain range of the device. So what we do here, we presented the left and right forces that he's putting on the device when he's supported. We can show here in the center the distance of his center of mass, the distance from the device, and we can actually use inertial sensors to show the posture that the user is right now to the person while walking. And then we can just provide visual cues so the person can be trained to better use the device or to achieve a certain partial body weight support strategy. So the idea here was we wanted a certain partial body weight support and a certain distance from the walker. And we did 3 experiments. The first one with no visual cue. The second one, we provided the visual cue, and then we remove the visual cue and try to see if the person learned this strategy. And what we can see here is we wanted this is just one example. We wanted the force to be concentrated in this area, and we are able to move here, of course, with the visual cue is easier. But when we remove the visual cue, again, the person learned how to use the device. And then we can just show some videos here. When the person is not in the correct position, the device would stop, but he does not have any visual cue here, so he just trying to figure out how he should walk and how he should behave with the device. And we can see that the device is stopping many times because he's not well positioned and he's not doing the partial body weight support strategy that we want. And then when we provide him with the visual feedback, he is able to very fast understand how the device should behave and how he should behave using the device. And here, again, it's important that the person applies a certain posture body weight support, because here we want him to discharge the lower limbs, right? And then here in the third video, we remove the visual cue, and the person actually learned these strategies. He's able to walk very easy in an easier manner and understand how the device should behave and how he should behave when using the device, and he's able to walk in a better manner. We are also measuring many parameters here which are under process. We are using EMG, we are measuring kinematics with inertial sensors. So we are making this into a more complex report that we should present in the following months. And again, here's the image. The person is not, in the first video, he's putting more force in one sensor than in the other. Sometimes he's not applying the right discharge strategy. Here we teach him how to use, and in the end he learned. So every step he's just placing the right forces and the correct partial body weight support strategy that we wanted. So I hope this presentation was enlightening to you. What we wanted to show is that it is possible to integrate many tools into the rehabilitation scenario, and we showed a little bit of our last developments and the past developments also of our group in rehabilitation robotics and assistive technologies. And I just want to thank you for your attention and leave here the funding and my thank you for the invitation to be here.